Hello, welcome to lesson 3 on equally likely outcomes, basic probability and poker hands. It's coming from the first few sections of chapter 2 from the textbook. We're going to start out with probability basic concepts. So, some definitions here. The definition of procedure or experiment is an action with possibly more than one outcome, usually more than one outcome for the examples we're going to do here. Flipping a coin, rolling a die, selecting a card. Now, the term sample space refers to the set of all possible outcomes of an experiment. So, in the case of flipping a coin, we have two possibilities, heads or tails. In rolling a single die, we have the face values 1 through 6. Selecting a card, we'd have, 52 possibilities there. We'll talk more about that case coming up. Now, an event refers to one or more outcomes of a sample space. So tails could be an event, two, or even number could be a sample. Even number is an event. It's multiple outcomes from a sample space. So the event even number would consist of three different outcomes, 2, 4, and 6, if we're looking at one die. Now, a simple event is an outcome or event that cannot be broken down into simpler components. So the previous example, even number, that can be split up. But something like tails, that can't be broken down anymore. That would be a simple event. So tails, heads, rolling a 5, those are all simple events. A notation, P parentheses A, that is read probability of A, probability of an event A. Any probability will always be between 0 and 1. 0 representing something that's impossible, and 1 representing something that is certain, 100%. The complement of an event A is denoted by A with a superscript C or A with a bar on top. And the complement is the opposite. All the other elements of the sample space other than the ones represented by event A. The complement of an event A is the opposite of A. All the other outcomes of the sample space, all outcomes in which A does not occur. So if A is the event rolling a 4 in a single die, the complement would be the remaining 5 possibilities 1, 2, 3, 5, 6. Now, one approach to computing probability is using real world data, relative frequency approximation. The number of times A has occurred divided by the number of times the procedure was repeated, the number of times A occurred divided by the number of trials of the experiment. Now, classical probability requires equally likely outcomes, and that is based more on some type of formula. So it's the number of ways A can occur divided by the number of different simple events in the sample space. So when you calculate classical probability, remember that you're doing a division process and you're dividing by the total number of possibilities. So in the fraction here, the number of ways that A can occur is your numerator. Your denominator is the number of elements in the sample space. Since A is taken from the sample space, it's inside of it, it's a subset, so it cannot be larger. A cannot be larger than S, so that expression, that fraction is either going to be one whole or it's going to be smaller. It's impossible to be bigger than one. How do we find the probability of the complement of A? So we use the fact that the probability of A plus the probability of A complement is equal to one whole or 100%. One of those things has to happen. It's a basically yes or no. Either the event A occurs or it doesn't, in which case the probability, the A bar, the A complement would be occurring. So the sum of those probabilities has to be one whole 100%. The probability of rain plus the probability of no rain is equal to 100%. One of those two things has to happen. Probability of rain, that's a good example of something that we would use a relative frequency approach there. We don't really have a formula for that, so we go based on the past to get a probability of a rain in a given location. So the example we have here, let me just highlight this here. We have the probability of 2 plus the probability of its complement, which would be 1, 3, 4, 5, 6. That has to equal 100%, one whole, because one of those 6 values is going to happen. Now, the probability of rolling a 7 on a single die, that's impossible. So that probability is 0. And the probability of the entire sample space S will always be one whole 100%. So the complement formula here, by subtraction, we get the probability of A bar, A complement, is 1 minus the probability of A. It's the opposite calculation, 100%, one whole minus the probability of the event A. Subjective probability, we're not going to do too much in this particular situation. It's estimated by knowledge of relevant circumstances. So, again, most of the course here will be working with classical probability. Occasionally, we may do some relative frequency examples. All right, so let's look at some examples here. Again, most of these are going to be classical probability using formula and equally likely outcomes. So we roll a single die. There are 6 possibilities. And based on the shape that all the surfaces are the same size, all 6 surfaces are the same size, each probability is the same. And so the probability of rolling any one of those values is going to be 1 out of 6. There's one way to get a 5 divided by 6 total possibilities. Rounded off is 0.1667. Rule of thumb for this course, typically 4 decimal places should be the most we're going to need. There may be some exceptions, but most of the time that's a good default to go to 4 places. But we may also leave things in fractional form. If we draw a single card from a standard deck, there are 52 total cards. What's the probability of selecting a king? So there are 4 of each value in a standard deck. So it's going to be 4 out of 52, which reduces to 1 out of 13 or 0.0769. Let me just scroll down here. I have a nice chart here. So there are 52 cards. There are 4 suits: a club, spade, heart, diamond. There's 13 values in each suit: ace, 2 through 10, jack, queen, king. So a grand total of 52 cards. There are 13 values in each suit, and there are 4 suits, so there are 4 of each value. There are 4 aces, 4 twos, 4 eights, 4 jacks, and so on. So the probability of a king is 4. There are 4 kings out of a total of 52. So that's 4 out of 52. Reduces down to 1 out of 13.0769. So if you want to find the complement, the probability of getting something else, probability of not a king, the complementary event, you're going to do 1 whole minus 4 out of 52, which is 48 out of 52, or 12 out of 13, which decimal form is 0.9231. And these values here, 0.9231, 0.0769, rounded off, but those values should total up to 1 because we have an event and its complement. The sum of those probabilities is always 1 whole. So again, just a summary here of the different features of a deck of cards: 52 total, 4 suits, 13 cards in each suit, 4 cards of each type or value. Diamond and heart are red cards. Those are half the deck, so that's 26. Club and spade are black, also 26. So the probability of drawing a red card would be 26 out of the total 52, which is 1/2, or 0.5. The probability of spade, that's 13 out of 52, which reduces to 1/4, or 0.25. Suppose the probability of rain on any day in a certain region is 0.30. So if the probability of rain is 0.30, what's the probability it doesn't rain? The remaining amount left over is 0.70. Remember, these have to add up to 1 whole. So 1 minus the probability of rain, 1 minus 0.30 is 0.70. Here is a little bit of a trick question. We're going to get to this in the next lesson. What is the probability of rain on Saturday or Sunday? And it does involve adding up, but you have to do a subtraction. So the correct answer is not going to be 30%, 0.30 for Saturday, 0.30 for Sunday. You have to do an extra step, but we'll see that in the next lesson. I put trick in quotes. It's a trick right now. We haven't learned that rule yet. But law of large numbers is something we're going to spend a lot of time on later in the course. Um, for now, we're just going to give the definition. As a procedure is repeated, the relative frequency probability tends to approach the actual probability. Repeated in this context means a tremendous number of trials. So if you're flipping a coin or rolling a die, you're not going to get the classical probability necessarily for a small number of tosses or rolls. But if you were to repeat the process millions of times, you would approach the classical probability. So you flip a coin 10 times, you may not get exactly 5 out of 10. You may get 1 or even 0 out of 10. It's unlikely but possible. But in the long run here, if you were to do this a million times, you had a million trials here, you'll probably be close to the classical probability, which would be 1/2. All right, let's see. Here we have a given chart here, results from a drug test of job applicants. So the person can test positive, test negative, and then we have the actual situation as to whether or not the subject uses the drug or does not use the drug. If a person tests positive and uses the drug, then that's a correct result. It's a true positive. In this case, there were 45 cases of that. Now, if you test negative, but you are using the drug or the subject is using the drug, then that's considered a false negative. That's an error. In this case, there were 5 of those. If you test positive and you're not using the drug, again, that's an error. That's a false positive. There were 25 here. If you test negative and the subject does not use the drug, then that's a true negative, 480 in this particular example. So if we want to find the probability of a false negative here, we want to take the number of false negatives, which is 5, and divide that by the grand total, which we'll have to add up those values. So in this particular situation, we're using a relative frequency approach here based on the results from this test. So the number of false negatives that occurred was 5. The total number of trials or test results, we have to sum this up, 45 plus 5 plus 25 plus 480. And that gives us 555 in the denominator. So it's 5 out of 555, which reduces to 1 over 111, and it's 0.0090. So the probability of a false negative here is 0.0090. What's the probability of a false positive? So we know the total. We know the total is 555. So that's our denominator is going to be 555. Now the numerator will be the number of false positives, which was 25. So this needs to be corrected here. Let me just make that change. So this is 25 out of the same 555. Which does reduce down to 5 over 111. Looks like that part was okay. And then converting to decimal form, 0.045. Just double check that. My apologies. Yes, that is correct. So it was just an error in the first part there, but everything is okay now. And again, these are errors. So a good test, you'd want to keep these errors small. So we have small probabilities: false negative 0.0090, a false positive 0.045. So again, in a testing situation, you want ideally for these errors to have a low probability. Now, next part here, what is the probability of testing negative? So to calculate testing negative, we have to add up the column here of the negative test results. So that's 5 plus 480. So that's going to be 485 divided by the grand total of 555. And that in decimal form is 0.8739. All right, back to the cards here. This problem's going to be a little bit more detailed here, going back to some of the counting techniques we did in the first 2 lessons. 5 cards are drawn without replacement from a standard deck of 52. Find the probability of 3 of one kind and 2 of another. So an example of this would be getting 3 jacks and 2 sevens. Just to see a physical example here. But again, we have to do a general count here. So how many ways are there to select 3 of any one value? You're selecting 3 from a total of 4 options for any one card value. So you're taking 3 out of 4 jacks, and then you're taking 2 out of 4 sevens. Now, the order here doesn't really matter. You can do this problem either way. There are situations where you can, when it's a probability question, you can treat it as ordered or unordered. As long as you're consistent in both the numerator and denominator, you will get the correct answer either way. Now, if you have a more complicated setup, then you have to be a little bit more careful. But in this situation, you could do it either way. So we're going to do this as a combination, mostly here. So the total number of possibilities is, without restriction, selecting 5 cards out of 52. So that's 52, choose 5, 52, C5. Now, the number of ways to get the 3 jacks or 3 of any value is 4, choose 3. And then you have to get 2 from a different value here, and that's 4, choose 2. So that takes care of the setup once you've fixed the values you want for the 2 um, repeated cards. The 3 of a kind is going to have one value, and then the 2 of another is going to have a different value. So now we have to run through all the possibilities here. It doesn't have to be jack and 7. So how many possibilities are there? There are 13 possibilities. There are 13 cards in each suit. There are 13 values. So there are 13 possibilities for the first triple, and then there are 12 for the 2 of another. And so that's going to lead to a 13 times 12 to take care of the different possible values we could have. So technically, that's a permutation. The order does matter, because if we switch the order, it would have been like having 3 sevens and 2 jacks, which is a different result. So in this particular piece of the problem, there is an ordered situation here in some respects. And so that part is 13 choose 12, 13p. It's 13p2, which is 13 times 12, indicating 13 choices for the first triple, and then 12 choices for the double or pair. So putting that all together, the numerator are the number of ways to succeed. So that's going to be 13 times 12 times 4 choose 3 times 4 choose 2. And then the denominator is the total, which was 52 choose 5. And then this reduces down to 6 over 4,165, decimal form 0.0014. So a very low probability of happening here. Again, you can use a calculator on exams. The Math Center will be able to provide calculators. All right, example 5 here. A die is rolled twice. Find the probability that the value of roll 1 is greater than the value of roll 2. We're going to take a little different approach here. Rather than listing out all the possibilities, we're going to kind of use a shortcut and summarize here. So we have, from the multiplication principle, a total of 36 possibilities. 6 for the first roll, 6 for the second. 6 times 6 is 36. Now, of those 36 possibilities, those 36 possible outcomes, there are 6 cases where we have a tie, that roll 1 is equal to roll 2 if we roll the same value twice. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So we can remove those, since we don't have roll 1 greater than roll 2 there. We're going to just we're going to remove those ties, and that leaves us with 30 cases where the values are unequal. Now, there's no reason why roll 1 should be greater than roll 2. It should be the same probability that the first roll is higher or the second roll is higher. So what we're going to do is divide that 30 by 2, leaving 15 cases where roll 1 is higher and the other 15 where roll 2 is higher, which gives us the 30. Again, the 6 ties we've removed. And so that leaves us with 15 ways to succeed here, divided by the total of 36. So the probability is 15 out of 36. Reducing by 3 is 5 out of 12. Again, you can do this out by listing, but it would be a little bit of a long process there. Depending on the value you get in the first roll, that's going to impact how many possibilities you have to win on the second. If the first roll is a 6, you have a lot of possibilities there to win. If you roll a 2, it has to be a 2 and then a 1. So again, you could list them all out, but this is a little bit more convenient. Example 6, a pair of dice is rolled. Find the probability the sum of the values is 7. So there are 36 outcomes here because we have a pair of dice, 6 times 6, 36. Now, the possible sums actually only run from 2 through 12, and those are not equally likely. It turns out that 7 is actually the most likely sum that is possible here with a pair of dice that are fair. So, how many ways are there to achieve this sum of 7? You could get 3 and 4 or 4 3. You can get 2 5, 5 2, 6 1, 1 6. So there are 6 ways to get the sum to be 7. Sorry, let me just move this down here. This is part of the solution. So there's 6 ways to win, 6 ways to succeed. To get a 7 divided by the total 36, and that reduces down to 1 out of 6. All right, this concludes the lesson 3 material. As always, please don't hesitate to email if you have any questions.